Hey everyone, and welcome back to another video. In this video, I'll be doing something very unique and unseen before. In this video, we are actually going to be performing an investigation and a statistical testing using Python. So basically, I have actually a topic that I want to investigate a little bit about and get an idea about. And I thought, why don't I do it on a video? So pretty much, I have a topic which is related to the stock markets, and I will try to kind of understand whether uh, a certain method of predicting future stock movements makes sense or not. So basically, if you have looked at machine learning and neural networks series of usually any YouTuber, you would have usually seen that they will always have some kind of a stock prediction project wherein they will go ahead and predict like the stock prices of any stock by looking at previous data, stuff like that. So, they look at previous data, and then they will go ahead and try to predict the stock price of that particular stock. What I'm trying to figure out is historic data enough or not? What that means is just historical data enough to predict a future price or not? Because if it is not, then all of those videos pretty much don't make any sense. But if it is, well, then it's good, right? Obviously, I know for a fact that the answer is no, not because I've worked this out before. It's just because whenever you watch any of those videos, you will always see that the model is simply not able to predict stuff. You will see that when we actually perform our statistical test, I actually tried this out a little while ago, and you'll see that the answer will be a very close to a yes, but you will see why that's the case. So without further ado, let's just head right into it, and let's actually first look at how can we actually approach this specific problem, and how can we actually understand how to predict the market. I'm sorry, how to understand whether just historical data is enough or not. So I'm going to just go to my iPad screen now, and I'm just gonna screen share that so you guys can also take a look at it. Should take just a second or two. First, I'm gonna explain you some basic concepts that I'm going to be using to do the things that I want to, and once I do that, we will jump into the actual video. So that's pretty cool, right? Alright, I'm just gonna mirror my screen real quick. It should take a second or two. There we go, perfect. So I hope you guys can see my screen now. I'm pretty sure you guys can. Alright, let me just increase my. Alright, I think that's good enough. Alright, so this is kind of what we have over here. As you can see, I have already worked this out for you. I have written a little bit of mathematics over here, but no need to worry. It's okay. It's actually relatively simple math. So here we have, first let's have a look at the problem statement exactly. The problem statement is given some stock data and some window like 60 days or 120 days or whatever. How accurately can we draw a linear regression line just by looking at this previous stock data? So basically, there are things now. If you have seen some, if I am assuming you know what linear regression is, but linear regression is just one way to do regression. There are several forms of regression, like linear regression, multiple regression. There's also, I think, polynomial regression and stuff like that. So it's not just linear regression that exists. There are several forms of regression. Now, usually you will have seen that in any machine learning playlist, they will always use linear regression to make these predictions. And the way the equation for linear regression works is just y is equals to beta plus alpha x, which is pretty much just the same, which is just the same as y is equals to mx plus c. And I'm pretty sure if you have done like basic high school math, like freshman year high school math, then you pretty much know what this is. uh, this is just the equation for the straight line. So this is the equation that we are working with. Now really what we want to figure out in this case is you want to calculate something known as the coefficient of determination between x and y. What is that, you may ask? So basically what the coefficient of determination tells us is whenever there is a change in y, what percent of the change in y can be attributed to the change in x. So you can understand why that's a very important statistic when we are trying to figure this out. Because if a very large percent of change in y can be attributed to change in x, well then this is really good, right? That's exactly what we want to try to figure out. So a lot of the times you will see that these machine learning algorithms, you will have seen those clickbaity titles that say 99.9% accuracy, 97% accuracy. Pretty soon I will show you that all of that's probably fake, and all of it is just completely overfit data, and it's just not correct. And you will see why developing efficient trading strategies is not something that you can do in an hour or two. Alright, so now how do we actually compute the coefficient of determination? So for that we first need to compute what is known as the Pearson's correlation coefficient. Now the Pearson's correlation coefficient measures the correlation between two variables. What does correlation mean? Let's look at that. So I've considered four lists of data over here. You can see it's just sets, four sets of data. So x is 1 to 3, y is 4, 5, 6, z is 5, 6, 4, and a is 27, 26, and 25. Now if you have done like even middle school math, then you know one very cool and important thing, which is proportionality between two values. Now I'm pretty sure in physics you would have seen a lot of equations like F equals ma, F is equals to g m over r squared. You would have seen all of these equations, and every time when we are trying to write those equations, we always say that F is directly proportional to m, F is directly proportional to small m, and F is inversely proportional to 1 over r squared. This means that if big M increases, F increases, small m increases, F increases, but if r increases, then F decreases. So all of this is just proportionality, right? And I'm pretty sure you guys already know that if two variables are directly proportional, it means that if one variable's value increases, then the other variable's value decreases. And that's pretty much what we know. But there's still a single problem with the concept of proportionality. It is that proportionality does not quantify the strength of the increase or the decrease in these two variables. So basically, let's say you have two variables, x and y, and the way they work, actually let's look at x and z in this case. You can see that over here we have x which increases and y that increases every time x increases, which tells us that x is directly proportional to y. But now if we look at x and z, you will see that if x increases, z does increase, but it only increases one time. But then when x increases again, z decreases. And if we look at x and a, well, they are just inversely proportional. So for x with y and for x and z, we know that x and y are directly proportional, x and a are inversely proportional. But what about x and z? Well, that's exactly where our middle school math breaks down, because in this case we need to quantify exactly how strongly proportional they are. And that pretty much is what the Pearson's correlation coefficient does, is it quantifies the strength of the correlation. That's kind of, I'm putting it in a little bit of vague terms. It's not like it's very similar to that, so that's how I like to put it. If you want to have like a very exact definition, then you can check it out on Google. You'll find a lot of pages on it. It's a very very popular thing, so you can check that out. All right, so now that we know what the correlation coefficient is, uh, let's actually look at exactly how it works. So the correlation coefficient can take up a range of values. So our R correlation coefficient can take up a range of values, which is going to be from -1 to 1, which is inclusive. A coefficient of 1 means it is the strongest positive correlation possible, meaning if one increases, other increases, and minus 1 is pretty much the opposite. Now, what does 0 mean? 0 means there is absolutely no correlation whatsoever. So that's pretty much what 0 means. So that's really all that Pearson's correlation coefficient tells us. Now, the reason why I actually showed you this, because I know a lot of you might be asking me, what is it, how does this link to what we are trying to do over here? Well, you will see that the way you compute the coefficient of determination is through the Pearson's correlation coefficient. So now let's see how we compute the coefficient of determination, which is denoted by the term capital R squared. I'm If you have studied like statistics, basic stuff, like when I say basic, I mean if you are getting like some, if you are in, I would say, junior high or something like that, junior high or senior high, maybe you would have seen all of this stuff already. Maybe not all of it, maybe not this portion, I'm guessing, but at least some of it. So if we look at r squared, which is the coefficient of determination, which we really want to calculate, it is just computed by squaring Pearson's correlation coefficient. That's literally all you have to do. And that's all we have to do. And then we can just multiply it by 100 to give us the percent that we want. Now, here's the cool thing. Here's the deal. Usually, if you look at the equation to compute the Pearson's correlation coefficient, you will see that it's actually pretty tedious to do it by hand. It's actually a pretty lengthy formula, and so no one really does it by hand because it would just take a lot of time. So all of this computation is usually done through some technology, maybe some sort of a GDC or maybe like Excel or Python or whatever it is. We'll be using Python. So we obviously need to figure out a good way to compute this. So we obviously need to draw some sort of a linear regression line. That's because one of the ways to the way you actually compute this is through that. So if you look at it, the way you compute alpha, which is the slope of the linear regression line, the way you compute it, it's r sy over sx. Sy is the standard deviation of the y, and sx is the standard deviation of the x. So that tells us that r is equals to alpha sx over sy, and so r squared is just alpha sx over sy the whole squared. This is supposed to be a upon, I just forgot to draw that. And if you know basic stats, you know that standard deviation squared gives you the variance. So you say alpha squared is equal to alpha squared times vx over vy times 100 gives you the r squared in percent format. So this is our final equation that we have for the r squared percent that we can obtain through code. So now that we have looked at the mathematics for today's video, let's jump into the code and now let's see if this works or not. Alright, so let's now start programming. I hope like you guys actually understood the math. If you did not, do let me know in the comment section, and I will definitely make some other video where I'll kind of go into all of this stuff a little more in depth, because this was really just to satisfy the mathematical rigor that we're going to need in this video. I didn't actually go into any other statistical concepts. Alright, so let us jump right in here. Let's open up a new terminal window, and I'm gonna cd to my desktop, and we're gonna make a directory stock prediction investigation. I don't know, I can't think of anything better, so oops. There we go, cd to that, and we can just actually open this up in a Jupyter Lab. There we go, perfect. And now we can get started working. We are gonna need a few libraries to do this, mainly just Yahoo Finance and stuff like that. So yeah. Okay, why is my Jupyter Lab taking so much of time to boot up? It usually is a little quicker. I think, I mean, I just turned my laptop on, so maybe that's why it's taking some time. Or maybe it's just frozen. Okay, there we go. I think we are done. Alright, perfect. There we go. You can just quit this. Alright, let's get started with the code now. I'll just create a new Python notebook and we can just rename this to main.ipynb. Alright, so let's start making the imports. I'm gonna import matplotlib.pyplot as plt. I will import. So now let me just show you the modules that we're gonna be using that I'm pretty sure that I think you won't have. So we're gonna be using a module known as Yahoo Finance. Actually, I think it's gonna be like Yahoo Fin. Yeah, this one. So perfect. This is the module that we're gonna be using. It is pip install Yahoo-Fin. Now I'm pretty sure you guys would be like, well, why? I'm pretty sure you guys would have you would say that you have heard the name of this specific package, but there are actually two packages that start with Yahoo and both are for finance. So you have to install this one. So it can do a lot of things. So yeah, just copy this command, paste it in your terminal, and install this. Alright, so now let's just start this. So import Yahoo Finance dot stock info as si, and we'll also import numpy as np and import pandas as pd. So now we need to specify some sort of a ticker symbol, so we'll just specify the snp, and then we can just say df is equals to si dot get data on the ticker. So then we can just get the head of the df, and you can see that this is from 1993. So I just want data worth 252 days, so we can then just say df is equals to df, and actually I only want the close prices, so we can just say close prices is equals to df close dot to list, and then we can just say, actually I don't want to convert it to a list, I just want it in numpy format. So nb.array close prices, and then we can just say close prices is equals to what should I do? Yeah, I have to. So we can just say close prices len of close prices minus days colon. That's pretty much all we have to do. So now if I get the len of close prices, you will see that it will just be 252. Now let me just show you what they look like. So we can just do a plot of the close prices, and there it is. You can just call a plot.show if you want, but that's not needed. Alright, so here we, as you can see, we have the plot of our close prices, which is looking pretty good. Alright, so now we have the close prices plot. Now we actually need to run some linear regression model on the close prices. For this, we'll be using sklearn or scikit-learn, which is a library for stuff like this. So I'll just say sklearn linear regression. So you can just get that. So I can see sklearn linear regression. This is exactly what we want. So we can just copy this and we can head on over here. Now we also need one more thing, which is known as the min-max scaler. Because the problem with our data right now is that our data is unnormalized data, and so we need to go ahead and normalize it first. So to do that, we'll make use of the min-max scaler. So sklearn min-max scaler. So as you can see, we have it right here, and we can just go ahead and copy this import, and we can get started working. So first we need to define the scaler. So we can just say sklearn min-max scaler, and then we have to specify what is known as a feature range, which is gonna be 0 to 1. I hope I have created this object correctly. oops, yeah, so we range 0 to 1. All right, and then we can just say close prices scaled is equals to scalar dot fit transform close prices, and we're gonna have to do one thing, which is just gonna be dot reshape, actually, dot reshape -1. That's okay, I just didn't spell it correctly. Close prices. Alright, so now you will see something cool is if I go ahead and plot the close prices scaled, you will see that our data lies from 0 to 1. But one cool thing is that the shape of the data does not change. So the data is pretty much the same, it's just scaled down. So that's pretty neat, right? Alright, so now we actually have our close prices scaled. So now we can create our trading day window. So we can just have our trading window, actually not window. So we'll just set it to 30. So for I in range from window to len of close prices scaled, we can specify our x and y train data. So x train, y train, there we go. Alright, now as you can see, I'm not really explaining exactly what I'm doing, but that's just because this is an investigation kind of a thing. It's not a tutorial. I explain the mathematics, but I won't be explaining a lot of the programming portion because I'm expecting this stuff to be known. Alright, so now let's start appending this. So xchain.append, and let's append the close prices scaled, and we want to start from I minus window to I think that should be good enough, and y train dot append is just gonna be equal to close prices scaled at I. I'm guessing that's good enough. So now we have to convert all of this into a numpy array. So x train and y train equals np dot array y train. So now if I get the x train dot shape and I get the y train dot shape, you can see that except for the 30, the number of feature, the number is same, so it's 222 and 222. So that means that our this thing worked, which is awesome. So now let's actually perform the linear regression. So let's head on over here. So we have our x and y data, so we can just copy paste this part now. So this will just say x train and this will just say y train. Now there is still one tiny problem, which is the fact that we are working with 3 dimensions, and I'm pretty sure that scalar linear regression does not do that. You need multiple regression for that. So we'll have to reshape it to x train dot shape 0, x train dot shape 1, and that's pretty much all we have to do. Alright, so if I just get the reg dot score x train y train, okay, what's the problem? Oh yeah, I'll have to reshape it again. Here's what we can do. We can just, oops, what happened? What we can do is we can simply copy that, put x train here, and we can just put it over, oops, x train. Alright, and now we can run this. So it is saying that we have a 95% accuracy. So this is an important statistic to keep in mind. Accuracy of linear regression model is, and we'll have to multiply it by 100%. There we go. So this is the accuracy as predicted by the linear regression model. Keep in mind that this accuracy is computed by calculating the residual, which is done by the MSE with the mean squared error, and then you just average over all the mean squared errors, and kind of that gives you the loss, and then you calculate the accuracy based on that, I'm pretty sure. So now we have the accuracy of our linear regression model. Now we actually have to compute the thing that we wanted to compute. So pretty much we want to compute the so this gives us the slope, I'm pretty sure. I want to get the coefficient of determination. I know that sklearn does have a thing for that to compute r squared. I just don't know how. Get params, predict, score. Yeah, so as you can see, for score it has xy sample weight returns the coefficient of determination of the prediction. So this is exactly what we want. So if I head on over here, you can see it's right here. So we can just say sklearn. I know that they actually have an example on that. Sklearn linear regression example. I know, so there is actually this thing, another page on the sklearn's thing. So here, as you can see, we have the coefficient of determination, but for that we actually need to make a prediction first. And the way I'm going to do this is very simple. What I can do is I can increase this to something like 454, and when I'm actually feeding in my X train and Y train, I can just feed in, let's say, the first, I can feed in half the samples. So I can just say len X train over integer divided by 2 in case we are going for an odd number of samples. And that's gonna be from the first to that. So we can just do that, and we can pass that into Y train as well. And now we're gonna have to do the same thing. So I'm guessing, you know what I'm gonna do is I'm just gonna do this and do this, just feed it in right in the beginning. So now I won't have to do that anymore. Right in here and right in here, it will just work. 11155. What's the problem now? Oh yeah, so I'm guessing this should be Y train. I'm guessing I'll have to run this again. Yep, now I think it should work. Alright, and now we can pretty much get rid of this. So now you can see it's 88%. Alright, so now let's actually go ahead and work on the r squared. So now we can have x test, which is just gonna be len. Oh, wait a minute. Why am I saying len x train over here? This should be len close prices scale. Actually, no, it should be len x train. So I think I should just make these x and y. X and make this y. And then over here, x, y. Pretty much doing the same thing, just a little differently. Alright, so now we can define our x test, which is just going to be x, and it's going to be and we will have to convert it to a NP array. So let's do that, and it's going to be x from len of x integer divided by 2 to everything, and y test is equal to NP array y len of, this is the capital X, capital Y integer divided by 2 test and y test. So we can just get the shape for x test and y test real quick. There we go, we get the shapes now. Alright, so now that we have the shapes, we can actually perform a prediction. So I can just head on to the example over here, and we can fit it to the I think we have already done that. Yep, so we have already fit the model, we just have to get the predictions now. So we can just copy this and we can paste it right here. So we can just say predict pred, and we can just pass an x test, and this is just going to be reg. Oops. Oh yeah, I'll have to reshape this. Not a big deal. Just do it super quickly. X test. Actually, I'll just do it in this specific code block. X test is equals to np dot reshape x test dot shape 0, x test dot shape 1. Done. All right. Cool. Now let's get the coefficient of determination. And this will say red and y test. R2 score is not defined. Oh yeah, I'll have to import that up top over here. So we can just actually, I'll do it in where I would actually imported all of the other sklearn dependencies. So just do that. Head on over here, and I want to put this in an f string format, so I'll just do it like that, because these docs were written like a relatively long time ago. I don't know if f strings were still a part of Python at that point, so we can just do that. And then we can just go ahead and multiply this by 100%. So you can see that the coefficient of determination is 83%, while the linear regression model says that the accuracy is 88%. Now if I do one more thing, which is that I get the mean squared error between y, wait a second, I think I screwed up something. Yeah, I made one tiny error. It's supposed to be y test and red over here. So now it's a lot closer, you can see. So we can just say y test and red over here, and we can just copy that. Print mean, actually we have to print it as an f string, mean squared error so now we have the mean square error. You can see that the mean square error is 0.003 for the test and the pred, but the coefficient of determination is just 0.87. So actually let me multiply this by 100 so you can get a better idea. You can see that the mean square error is just 0.34, because if I go ahead and plot the y test and if I plot the pred, plot.show, you will see that it's really close, but the coefficient of determination says otherwise. You can see that 13% of changes are not attributed to this, and that can be confirmed by the linear regression model, which also says that a 12% change. But the problem right now is that it's the mean squared error that we need to look at, because that is a statistic that everyone refers to when training some sort of a neural network, is what is the mean squared error statistic. And if the mean squared error says that it is 0.34, but the coefficient of determination is just 87, it should be 99.7, because that would mean that 0.3% of changes are not due to the previous data, which means that the model has pretty much done its best. That's my interpretation. I might be wrong on this one, but I am saying that an 87% coefficient of determination means that there is a lot of room 13% chance that 13% of the changes, so there's a 13% chance that whatever changes that happen in the stock markets are not going to be due to past historical data. And this is just using 1 year's worth of data. And we are looking at something like the S&P. If we were looking at a more volatile stock, then this entire thing would be a lot different. You know what, let's try something out. I'm gonna enter some a little more volatile stock. uh, let's search for something. I don't know, Nasdaq penny stocks. I want to look at a couple of very small penny stock. MULN, never heard of it. Let's try it out. Alright, I'm guessing it's a penny stock. I don't know if it is or not. As you can see, it has fallen considerably from its market. And there you go. There you go. You can see that definitely the mean square error is very, very high, and the accuracy of them, you can see that the coefficient of determination is so bad. And there you go. So that's pretty much it. So and the reason why this has happened, and actually to be honest, this is not a good thing to look at, because we were looking at things, prices where they were this high, but then we are predicting at this level, so I can't look at this stock a lot nicely. Alright, I know that Rivian could be a good one. Rivian share price. Actually, let's try Tesla. I think, Tesla has been super volatile, like in terms of, I think Tesla and Nvidia could be good companies for what it is that we are trying to figure out. So you can see that the mean square error is 0.11, and the coefficient of determination is 95%, which means that the movements are dependent. But let me actually show you something. So if I zoom in here, you will see that our model, it can accurately follow trends, but it can't accurately create trends. You can see that when there was a downtrend, our model did go down, but it took us a one upward movement in order for our model to follow. But you can see that there was a 1 day worth of difference over here. So but by that time our thing had started falling down again. But what had happened is that for our model, this is just a slight loss. This isn't something considerable. And that's kind of what it has been doing every single time, is that it cannot fall, it cannot create trends. So if I actually give these labels, label Y actual and I'll make this a little larger. Now you can see that it can not accurately create trends, which means that it is not good enough. And even though we have a large coefficient of determination in this case, you can see that we still have a mean square error. Technically, I think that the mean square error and coefficient of determination should be very close to each other, but they are not. So that means that there are several factors apart from previous historical data that contribute to the markets, and therefore it will be an incredibly unsmart decision, I would say, an incredibly dumb decision to actually just look at previous data to in order to predict future prices. Now you might say that I have personally done that kind of things in the past, and there are two reasons for that. In fact, one of my videos I did say that the reason why I did that is because I was continuously running into several errors when I was trying to do multiple regression and multiple feature neural networks, and that was the only reason why I did that. I think I did say that in one of my videos, and in another one of my videos when I was doing it, I simply did not possess the knowledge myself. and I have to apologize for that. I mean, I'm trying to produce content that is educational and stuff, but yeah. So that simply that I am sorry for that. But now that I've figured out that it is incorrect, I hope that even you guys understand that this is not the way you should trade the markets. Realistically, you'll be using a lot more than just historical data in order to trade this. So I hope that this video was somewhat of an eye opener for anyone who's trying to figure this out. It would be a great project to understand how neural nets work, in a practical sense, but it definitely is not a good project to actually put to the test. So that's it for this video. I hope you enjoyed it. If you did, like and subscribe to the channel, and let me know in the comment section